Ever felt like you're just drowning in information when you try to learn about some complex tech topic?
Yeah, us too. That's really why we do the deep dive. We try to cut through all that noise, get you the core insights you actually need, fast. So today we're diving into the really fascinating world of microservices communication. If you've ever used something like Netflix or Amazon and wondered how those complex apps just work behind the scenes, how they deliver that smooth experience, well, this deep dive is definitely for you.
It really is, because at its heart, a microservices architecture means breaking down a big application into um, lots of smaller independent bits, components. Think of each one like a specialist. One handles user logins, maybe another processes payments, another keeps track of inventory. But, and this is the absolute key for the whole thing to work together, these separate services have to communicate. They need to talk. Yeah, it reminds me a bit of like a really efficient factory floor. You've got different workers or maybe workstations, each doing one specific job, assembling a part, checking quality, packing the box. But they absolutely have to pass materials and instructions back and forth, in a coordinated way. If they can't communicate, the whole line just stops. So, our mission for this deep dive is pretty clear. We want to unpack why this communication is so critical. It's not optional. We'll explore the common ways these services talk, look at the really powerful tools Java and Spring Boot offer to make it happen, and, importantly, help you figure out how to choose the right communication approach for different situations.
Exactly, because effective, reliable communication, that's really the backbone. It's what makes the whole microservices idea work and gives you that seamless experience you expect.
Okay, building on that, let's really get into why they need to talk. You said they're independent, but clearly not totally separate. They have to exchange information all the time to give us that cohesive experience, right? Like,
Mhm.
take an e-commerce app. The order service must talk to the payment service. Has to.
Absolutely, to confirm the transaction. And when they talk, there are really two main styles, two main types of communication. First, you've got synchronous communication. Think of it like making a phone call. One service sends a request, and it literally waits right there for an immediate response back. This is really common for things you need an answer for now, like checking if a product is actually in stock before you let someone buy it. Then the other style is asynchronous communication. Now think more like sending an email or maybe dropping a package in the mail. One service sends off a message, but then it just carries on with its own work. It doesn't wait for an immediate reply. This is incredibly useful for stuff like, say, sending out order confirmation emails or notifications. The response isn't needed that exact second.
That phone call versus email analogy really helps clarify it. Makes sense. But okay, even with these different styles, it sounds like just getting two separate pieces of software to talk reliably over a network that must have its own challenges, right? What kind of pitfalls do teams hit?
Oh, definitely. It's not all smooth sailing. The sources really highlight some key things, network delays, for instance, or outright failures that can disrupt communication. And then there's the complexity of keeping data consistent. If the order service updates, but the inventory service fails before it gets the message, how do you handle that?
Right, that data consistency across different services sounds like a really thorny problem.
It is, and just coordinating lots of services adds complexity overall. It's not trivial.
Can you give a concrete example, maybe from one of those big companies?
Sure, Netflix is a great one. When you open the app, their streaming service needs to talk to the user profile service.
Wow.
It fetches your viewing history, your preferences. That's how you get those personalized recommendations. That's typically synchronous communication right there. It needs that info now to show you the right screen.
Okay, got it. So we know why they talk and the basic styles, sync versus async, and some of the challenges. How do they actually do it in practice? Are there established ways, like blueprints or patterns, for these conversations?
Absolutely. Microservices rely on specific communication patterns, and each is suited for different needs. The first, and maybe the most familiar one, is request response. This is usually synchronous. So one service sends a request, often using something like HTTP, like a REST API call, and waits for the reply. Think about logging in. Your app sends credentials to the authentication service, it checks them, and responds immediately. Yes or no. The big advantages. It's simple, you get that real-time feedback, and most developers know REST pretty well. But the downside, if the network is slow or the other service is overloaded, the calling service is just stuck there waiting. It creates a kind of tight coupling.
Okay, request response is simple, familiar. But yeah, that waiting part sounds like it could be a real bottleneck, especially for apps with lots of traffic. Is that where the asynchronous event-driven approach really comes into its own, by sort of sidestepping that waiting game?
Exactly. That leads us to event-driven communication, which is inherently asynchronous. Here, instead of one service directly calling another and waiting, A service publishes an event, basically a message, saying, hey, something happened, usually to a central message queue or a broker, and then it just moves on. Other services that care about that event can subscribe and react to it whenever they're ready. They don't interact directly back with the original sender immediately.
Ah, so it decouples them. The sender doesn't even need to know who's listening, potentially.
Precisely. That decoupling is a huge win. It improves scalability, makes the system more resilient to failures. If the email service is down temporarily, the order service doesn't care, just sent its event. The challenge, though, can be that it's sometimes harder to track what's happening across the system, harder to debug, because the communication is indirect.
Makes sense. Can you give an example of event-driven?
Sure. When an order is placed, the order service might publish an order-placed event. The inventory service listens for that event and updates the stock levels. The shipping service listens and starts preparing the shipment. The notification service listens and sends an email. All triggered by that one event, but working independently.
Right, and I can see how publish subscribe builds directly on that. It sounds like the formal name for that pattern where one event goes to many listeners.
Exactly. Publish subscribe, or pub/sub, is a specific type of event-driven pattern. One service, the publisher, sends a message to a specific topic. And then multiple services, the subscribers who are interested in that topic, all receive a copy of the message. Think about a general notification service. It might publish a new feature announced event. Then the email service sends an email. The push notification service sends a mobile alert, maybe an in-app message service displays something too. One event, multiple actions.
Okay, request response, event-driven, pub/sub. What about this API gateway pattern? It sounds a bit different, less about service-to-service talk and more about how clients interact with the whole system.
That's a good way to put it. The API gateway acts as a single front door, a single entry point for all incoming requests from clients like web browsers or mobile apps. Instead of the client needing to know the addresses of, say, 10 different microservices, it just talks to the gateway. The gateway then intelligently routes the request to the appropriate backend service. It can also handle common tasks like authentication, security checks, rate limiting, maybe even transforming requests.
Ah, so it simplifies things immensely for the client developer. They just see one API.
Exactly. And it provides a central place to enforce policies. Amazon is a classic example. When you use their website or app, your requests likely go through an API gateway. It figures out if you're searching products, adding a cart, checking out, or managing your account, and sends your request to the right internal service. Makes it all feel like one unified application to you. And often, real-world systems use a mix of these patterns. Uber, for instance. They might use a synchronous request response call to quickly check nearby driver availability, but then use asynchronous events, maybe pub/sub, to notify the payment service once a ride is completed, and also to send a notification to your phone. Choosing the right pattern, or combination of patterns, really depends on what you need for that specific interaction speed, scalability, reliability, decoupling.
Okay, this is great. We've got a solid grasp on why microservices communicate, the different styles, the core patterns like request response, event-driven, and the role of the API gateway. So the big question for a lot of our listeners, especially those working with Java, is how do you actually build this stuff using Java and Spring Boot? What tools does that ecosystem offer?
Yeah, and the good news is the Java and Spring Boot ecosystem is really rich here. It provides excellent tools for all these patterns. For that fundamental synchronous or request response pattern using REST APIs, you've got Spring Web, specifically modules like Spring MVC or the newer Spring Web Flux if you need reactive programming. This is really the bedrock for building your HTTP endpoints, creating the APIs that your services will expose. It makes it quite straightforward. A classic example, a user service exposing a user's endpoint that the order service can call to get user details, built with Spring Web.
Okay, so Spring Web helps you build the REST APIs. But what about calling them? If my order service needs to call that user service API, what's the best practice in Spring? I hear Spring Cloud OpenFeign mentioned a lot.
Right. So while you could use a basic HTTP client like Spring's REST template or web client to call another service's REST API, Spring Cloud OpenFeign makes it much, much cleaner, especially for service-to-service communication. It's a declarative REST client. You basically define a Java interface that mirrors the API you want to call, add a few annotations, and Spring Boot handles the rest. It wires up the implementation, handles things like converting your data to JSON, and crucially, integrates with service discovery and client-side load balancing if you're using tools like Eureka or Console.
Ah, so it hides a lot of the boilerplate network code and makes calling another service look almost like calling a local Java method.
Exactly. It significantly reduces the code you need to write for synchronous calls and makes it more robust. An order service using a Feign client interface to call inventory service.checkstock productized is way simpler and less error-prone than manually building HTTP requests.
That makes a ton of sense, especially as the number of services grows. Okay, so that covers synchronous well. What about the asynchronous event-driven side?
For asynchronous event-driven communication, the key player in the Spring ecosystem is Spring Cloud Stream. This provides a really nice abstraction layer over different message brokers like Apache Kafka or RabbitMQ. You write your code against Spring Cloud Stream's concepts, like sources, sinks, processors, bindings, and it handles the specific details of interacting with the broker underneath. It simplifies sending and receiving messages tremendously and supports patterns like publish, subscribe naturally.
So if I want my notification service to send alerts using Kafka, I'd use Spring Cloud Stream.
Yes, absolutely. You configure your application properties to point to your Kafka broker, define a binding for your output channel, and then just inject a stream bridge or use functional handlers to send your messages. Spring Cloud Stream takes care of serialization, topic management, etc.
Okay, Spring Cloud Stream for abstracting over message brokers. You mentioned RabbitMQ. Is there also a specific Spring tool just for RabbitMQ, maybe for more direct control? I think I've seen Spring AMQP.
You're right, there is Spring AMQP. While Spring Cloud Stream can use RabbitMQ as a binder, Spring AMQP provides a lower-level, more direct integration specifically with the AMQP protocol, which RabbitMQ uses. If you need really fine-grained control over RabbitMQ features like specific exchange types, complex routing keys, dead letter queue configurations, manual acknowledgements, Spring AMQP gives you that deeper access. So you might choose Stream for simplicity and portability across brokers, or AMQP if you're all in on RabbitMQ and need its advanced capabilities. An inventory service receiving order updates via RabbitMQ might use Spring AMQP for precise control over message handling.
Gotcha. Stream for abstraction, AMQP for deep RabbitMQ control. And what about the API gateway pattern? Does Spring have a dedicated tool for building that front door?
It does. That's Spring Cloud Gateway. This is the modern Spring project specifically designed for building API gateways. It's built on Spring Webflux, the reactive stack, making it non-blocking and highly scalable. It allows you to easily define routes, mapping incoming requests based on path, host, headers, etc. to the correct backend microservices. Plus, it provides built-in filters for adding logic like security checks, rate limiting, request response modification, and integrating circuit breakers.
So it handles that routing and the cross-cutting concerns we talked about earlier, like security.
Exactly. It acts as that central enforcement point and simplifies your backend services because they don't all need to implement, say, authentication logic themselves.
Wow, it really is a comprehensive toolkit. Spring Web, OpenFeign, CloudStream, AMQP, Cloud Gateway. It seems like Spring Boot really has you covered for these core communication patterns.
It really does. And the beauty is they're all designed to work well together within the broader Spring ecosystem, which makes development significantly easier for Java teams building microservices.
Okay, so those core Spring tools handle the main ways services talk, but building robust, large-scale systems, it usually involves more, right? It's not just about sending the message, it's about handling failures, dealing with huge volumes of data, understanding what's actually happening when things go wrong. What other tools or strategies do the sources mention that really enhance microservices communication, especially as systems scale up?
That's a crucial point. Beyond the basics, several other tools and practices become essential. For really high-throughput, highly resilient, event-driven systems, Apache Kafka itself is often the message broker of choice. While Spring Cloud Stream abstracts it, understanding Kafka's own capabilities is important. Kafka is a distributed streaming platform. It's designed for handling massive strings of events, storing them reliably, and allowing multiple consumers to process them independently. Think millions of events per second. Companies like Spotify use Kafka extensively, for instance, to stream song play events, to power things like real-time recommendations or artist royalty calculations. Spring for Apache Kafka offers deep integration if you need it.
Right, Kafka for massive scale eventing. And you mentioned failures earlier. That synchronous call, the phone call, what happens if the line is busy or just drops? How do you make those calls more resilient?
That's where libraries like Resilience4j come in. This is a lightweight fault tolerance library, specifically designed for Java 8 and functional programming styles. For those synchronous calls, maybe made using Feign or web client, Resilience4j provides patterns like circuit breakers. If a service keeps failing, the circuit breaker trips and automatically fails subsequent calls fast, preventing your service from getting bogged down waiting for a failing dependency. After a while, it tries again, retries, automatically retry a failed call a few times in case it was just a temporary network blip. Timeouts, Limit how long you're willing to wait for a response.
So Resilience 4J basically builds in defensive mechanisms against flaky downstream services or network issues.
Exactly. It stops one failing service from causing a cascade failure across your entire system. It's absolutely essential for production-grade synchronous communication. A service retrying a failed payment call during a brief network issue is a classic Resilience 4J use case.
Okay, that handles preventing failures. But when things do go wrong or even just get slow in a system with potentially dozens of services talking to each other, how on earth do you figure out where the problem is?
That's the challenge of distributed systems. And the answer is distributed tracing. Tools like Spring Cloud Sleuth for instrumenting your Spring Boot apps, and Zipkin or Jaeger or other compatible backends for collecting and visualizing the traces are key here. What Sleuth does is automatically add unique IDs, a trace ID for the overall request, and span IDs for each step to requests as they pass from one service to another. These IDs are propagated across service boundaries, usually in HTTP headers or message headers. Zipkin then collects all these time spans and stitches them together, giving you a visual timeline of exactly how long a request spent in each service, where the bottlenecks are, and where errors occurred.
So it's like getting a detailed map and timetable for every single request journey through your microservices.
Precisely. It provides crucial observability. Netflix, again, uses distributed tracing heavily to understand and debug latency issues between, say, their main API gateway, the video streaming service, and the user profile service. You can pinpoint exactly which service call is slowing things down.
That sounds indispensable for complex systems. Okay, so we have advanced tools like Kafka, Resilience 4J, Sleuth Zipkin. What about fundamental practices, things you just have to get right?
Yes, several critical considerations come up repeatedly in the sources. Data formats. Choosing the right format matters. Lightweight formats like JSON are standard for REST APIs. For event streaming with Kafka, binary formats like Apache Avro are often preferred because they're more compact and support schema evolution, which is crucial for decoupled systems. Security. This is non-negotiable. APIs need protection. Using standard protocols like OAuth 2 or JWT JSON Web Tokens to secure communication between services is vital. Spring Security provides excellent support for implementing these. Latency. You always need to be mindful of network delays. Strategies include optimizing your API calls, don't fetch more data than needed, perhaps using more efficient protocols like gRPC for internal communication where appropriate, and definitely leveraging asynchronous communication for tasks that don't require an immediate response. Monitoring. Beyond tracing, you need basic health monitoring. Spring Boot Actuator is fantastic for this. It provides built-in endpoints, actuator health, actuator metrics, etc., that give you insight into the health and performance of each individual service. Monitoring tools can scrape these endpoints to give you dashboards and alerts.
So it's a combination of powerful specialized tools and getting these core practices right: data formats, security, latency awareness, and constant monitoring.
Exactly. These tools and practices work together to ensure your microservices communication is reliable, secure, efficient, and importantly, understandable, even as the system grows in complexity.
Okay, this is where it all comes together, I think. We've laid out this whole landscape: the why, the patterns, the core Spring tools, the enhancing tools and practices. But for someone listening, maybe an architect or a developer planning a new system or refactoring an old one, the big question is, how do I choose? With all these options, how do you pick the right tool or pattern for my specific situation?
That's the million-dollar question, right? And the answer, as always in tech, is it depends. But we can definitely provide some strong guidelines based on common scenarios. Let's break it down by tool. When should you use Spring Web, REST APIs? This is your go-to for simple, synchronous, real-time communication. If Service A needs information from Service B right now to complete its task and the interaction is relatively straightforward, REST is often the simplest and most widely understood approach. Think user authentication, looking up product details, checking basic status.
So standard request response where immediacy is key and complexity is relatively low.
Exactly. An e-commerce app, checking inventory when you add an item to the cart that's often a synchronous REST call. Needs to be fast, needs an immediate answer. Now, when do you bring in Spring Cloud OpenFeign? You use OpenFeign on top of Spring Web when you're doing those synchronous REST calls between your own microservices. If you want cleaner client code, less boilerplate, and built-in niceties like integration with service discovery and client-side load balancing, OpenFeign is the way to go. It makes internal synchronous calls much easier to manage and more robust.
So it's for simplifying and strengthening those internal synchronous calls.
Precisely. A booking service calling a payment service using Feign for a seamless checkout process that's a perfect fit. You get resilience features and cleaner code. Okay, shifting gears to asynchronous. When do you reach for Spring Cloud Stream with Kafka or RabbitMQ? You choose this for asynchronous event-driven communication, especially when, through one, decoupling is important. The sender shouldn't need to know about the receiver. Two, you need resilience against temporary receiver unavailability. Three, you expect high throughput or need to scale producers and consumers independently. Four, you have a one-to-many communication need, like pub/sub.
So think decoupling, scalability, resilience for non-immediate tasks.
Absolutely. Uber sending ride completion events to billing, notifications, and driver rating services that screens event-driven architecture using something like Kafka, managed via Spring Cloud Stream. And when is Spring Cloud Gateway the right choice? You implement an API gateway using Spring Cloud Gateway when your system has multiple microservices that need to be exposed to external clients. Web apps, mobile apps, third parties. It provides that single point of entry, simplifies the client's view of the system, centralizes cross-cutting concerns like security and rate limiting, and handles routing.
So essential for almost any non-trivial microservices system that has external users or APIs.
Pretty much, yes. Think of Amazon's website again. That single interface hiding dozens or hundreds of back-end services relies heavily on a gateway. And finally, those enhancing tools, Resilience 4J and Sleuth Zipkin. Honestly, you should consider these almost mandatory for production systems. Use Resilience 4J whenever you have synchronous communication to build in fault tolerance. Circuit breakers and retries are vital. Use Sleuth Zipkin whenever you have more than a couple of services talking to each other to get that crucial observability and debugging capability for distributed tracing. Netflix tracing user requests is a prime example of needing this visibility.
That's a really clear breakdown of when to reach for each specific tool. Beyond that, are there maybe some general rules of thumb or guiding principles the sources suggest for making these choices?
Yeah, definitely. Some good general guidance emerges. First, start simple, especially for smaller apps or teams new to microservices. Don't immediately jump to the most complex event-driven setup if a simple REST API with Spring Web will do the job initially. You can always evolve.
Right, avoid premature optimization or complexity.
Second, scale with async. As your application grows, especially in terms of traffic or the need for decoupling, seriously consider leveraging asynchronous communication with Spring Cloud Stream and a robust broker like Kafka. It's built for scale and resilience. Third, add resilience. Always. This is maybe the most important one for production. Integrate Resilience 4J for your synchronous calls. Assume failures will happen and build defenses against them from the start. It's not an afterthought.
Non-negotiable, basically.
Pretty much. Fourth, monitor everything. Use Spring Boot Actuator for health checks and metrics. Implement distributed tracing with Sleuth Zipkin early on. You can't manage or fix what you can't see. Observability is key. And finally, consider your team's skills. Choose technologies your team understands or can learn effectively. While Kafka might be powerful, if your team is more comfortable with RabbitMQ and Spring AMQP, that might be a better starting point. The good news is the Spring ecosystem is generally well documented and has a huge community, making learning easier.
That's fantastic practical advice. Start simple, scale async, build in resilience, monitor everything, and play to your team's strengths.
Exactly. Following those principles, along with understanding when to use each specific tool, puts you in a great position to design effective communication strategies. So wrapping up this deep dive, it's really clear that microservices communication isn't just some implementation detail, it's absolutely fundamental. It's the key to building applications that are scalable, that are reliable, that are maintainable in the long run. And the Spring Boot ecosystem, as we've seen, offers this incredibly robust, comprehensive set of tools to handle it all from Spring Web and OpenFeign for those synchronous needs, right through to Spring Cloud Stream for event-driven patterns, and Spring Cloud Gateway for managing that crucial entry point.
Yeah, and by carefully matching the right tool and the right pattern to what your application actually needs, are you prioritizing real-time interaction or is asynchronous processing okay? Is simplicity more important right now, or do you need massive scalability from day one? You really can design communication strategies that are just as effective as the ones used by the big players we talked about, like Netflix, Uber, and Amazon. So thinking about all this, what does it mean for you listening right now? Does understanding these intricate communication patterns, these layers of tools and resilience, does it change how you look at those incredibly smooth apps you use every single day? Maybe it makes you wonder what unseen complexities, what careful balancing acts between speed and consistency are happening behind the scenes just to make your experience feel so effortless. What trade-offs are made? Keep exploring those questions. Keep asking how things work. Keep digging deeper. It's a fascinating world out there.